first question here is, oh, I'm on the very last one. Hang on just a sec. The first question here is page 418, number 9. And the question here in particular says, why are they using cross product? So if we're looking for any vector that's perpendicular to two other vectors, so perpendicular to two vectors, that's the cross product. So if we're kind of looking for a third vector, I guess, perpendicular to two other vectors, that's going to be the cross product. If you're looking for one vector perpendicular to another, that's where we have dot product equaling to 0. But those are two kind of separate cases. So in this case, we're looking for a third vector and it's perpendicular to these two vectors. So the 0, 3, -5 and the 2, 3, 1. So we're looking for a third vector that would be perpendicular to both of those, and we're also looking for a unit vector. This where I always do say perpendicular vectors means the dot products equal 0. That's two perpendicular vectors, but if you're looking for one vector, a third vector that's perpendicular to two given vectors, that's going to be your cross product. So here I'm going to do the cross product of those two vectors. So I'll have 3 minus -15, which is 18. -10 minus 0, so just -10, and 0 minus 6, which is -6. So if I just had, like, say, A cross B, that would be 18, -10, -6. And then I want to figure out what the magnitude of that is. So I'm just going to use the regular magnitude formula. That's a square root of 18 squared plus -10 squared plus -6 squared. And I just realized that I don't have a calculator handy. Does anybody have a calculator with them? I'm just going to mute this for a second and run and grab one. Here we go. Sorry, I'm not at my normal desk, but there's a lot of calculators in my house. So 18 squared plus 10 squared plus 6 squared is we've got square root of 460. So the unit vector is 1 over root 460 times the given cross product. So that'll be 18 over root 460, -10 over root 460, and -6 over root 460. You could rationalize those, but you don't have to. I wouldn't take off marks if you didn't rationalize the denominators there. I think that's fine to leave it like that. Any questions on that one? Oh, thank you, Gina. Okay. Here we've got an object with a mass of 10 kilograms. Next one is page 418, number 6. And this is one of those tension questions. So we know we're always going to set this up the same way. We've got the force of gravity going down, and the magnitude of that is 10 times that 9.8, so 98 newtons going down. And we have two different ropes. One makes a 30-degree angle, and one makes a 45-degree angle. And I do like this one because if you remember, a couple of the examples had that bottom angle kind of by the force of gravity equaling to 90, but it's really not usually 90. And it's a bit misleading, I think, to have examples where it is. So I'm glad that this one does not have that. So we're going to have two forces, one in each rope, that will counterbalance or be an equilibriant force to the force of gravity. So if I redrew this, I would have F1 in that direction and F2 in that direction, and that they would add up to that resultant force, and the magnitude of the resultant is going to be the same as the magnitude of the force of gravity. So then what we really need to do is to figure out what those, what the angles in this triangle are going to be, because then we can find the magnitude of that. So I would know that when I subtract there, if I subtract the 30 and 45 from 180, then that is going to be 105 degrees at the base there. Okay. I can also look at this sort of as like a C pattern there, like that would make a C pattern. And that can give me, there's different ways to look at this for sure. But I would get that is going to be 75 degrees. I can take a look at creating a right angle here. And then I would know that this angle is 45 because they would add up to 180. So then this is going to get very messy and colorful here, that we could see a Z pattern. If you see where I'm highlighting in green there, that would show I have this 45-degree angle up at the top. And if I subtract, I could either subtract from 180 on that new triangle that I've drawn and figure out the base, or I could look at the left-hand triangle in the original picture and see that that would have to be a 60 degrees. Both ways work. So whatever you have to do to figure out those angles, there's a number of different ways of looking at this, and I'm just going to kind of redraw it a little bit less messy. So I've got the magnitude of F2, the magnitude of F1, I've got this resultant that's 98 newtons, and here I've got 75, 45, and 60 degrees. So once you have this triangle set up, then you're just going to do the sine law. I know all of the angles. There's no ambiguous case here. So I'm just going to say the magnitude of F1 over sine 45 is 98 over sine 75. And pop that into my calculator. So I get that force is 71.74. And then the magnitude of F2 over sine 60 is 98 over sine 75. So again, sine 60 times 98 divided by sine 75. there I get the second force of tension is 87.86. Making sure you're answering word problems in a sentence using your units. So I've got this in newtons. So I could say, therefore, the tension, or the force of tension, you could write that out, in the, now F1, I'm going to call the 30-degree rope, is 71.74 newtons. And in the 45-degree rope is 87.86 newtons. Everybody okay with that one?
Miss Cooper?
Yes.
So in your first triangle you drew, the angle between F1 and F2 was 60 degrees. Why wasn't it 60 degrees in the second triangle?
The angle between F1 and F2.
Yeah, I don't know how to describe it.
Like there?
Yeah, that angle.
Okay, so that came from like this half of this triangle, saying like if I dropped a perpendicular, like a vertical line there, that I'd have a 90 degree here, and 30 and 60 and 90 make 180. So that came from here. So that is that 60 degree angle there. But this whole angle between F1 and F2 where they're tail to tail, that's actually 105. Because that would be looking at the big outside triangle with the 30 and 45 at the top and subtracting those from 180. So that whole angle at the bottom there is 105.
Okay, that makes sense.
Okay. Okay. So the next one, page 418, number 10, couple kind of notes here. What do you need to use? Why do you need to use alpha, beta, and gamma in this question? Sorry, guys, switch slides. What's the purpose of these symbols? We don't actually have to use any particular, you could use any angle variables. That sounds, I'm not sure where somebody saw that solution. I don't know if whoever put that is logged in. That feels like something that the textbook would do in their solutions, likely more than me. But I would say that if you had these points, like A, B, C, that I would want to figure out what are each of these vectors. So I would find like AB, AC, and BC. It doesn't really matter which vectors you find, but I would figure out what each vector would be. So AB is going to be -2, -6, -3. AC is going to be 3. 2 minus 3 is -1. And -4 minus 7 is -11. And BC, 5, 5, and -8. So I think I've got those correct. And then I would want to find the magnitude of each. So I would say the magnitude of AB would be square root of -2 squared plus -6 squared plus -3 squared. And that's 49, which of course we can take the square root of, but I'm just going to leave it as is for a minute because I really want to be able to compare here. So then the magnitude of AC will be the square root of 3 squared plus -1 squared plus -11 squared. And that will be the square root of 131. And then the magnitude of BC is going to be the square root of 5 squared plus 5 squared plus negative 8 squared. So that's the square root of 114. So if we label these, and AB was root 49, and AC, whoops, other way around, AC was root 131. We know from trigonometry that the biggest angle is going to be across from the biggest side. So we don't have to find all of the angles in the triangle. I would just find angle B. So I'd say let theta be angle B, like the angle at point B. And then I would use the cosine law. So we would know that cos B is going to be root 49 squared plus, I'm just going to reset to get myself a bit more room, plus root 114 squared minus root 131 squared over 2 times root 49 times root 114. So you can put that all into your calculator. And I get angle B is 77.64 degrees. So then we want to determine the area of triangle ABC. So remember the area of a parallelogram? I think in the solutions with how I've drawn it up, I would do for B, I'm not going to have room to write this all out. I'd say area is 1/2 the magnitude of AB cross AC. But there's a good question here. Can you use, for example, BA and BC to do that? And yes, you can, as any two vectors that are tail to tail. They have to be tail to tail. So my example had 1/2 AB cross AC. You could also do 1/2 the magnitude of BA cross BC. And so with that, you would be doing like vectors going from B, or you could do 1/2 the magnitude of CA cross CB. So as long as you're making two vectors along the triangle edges that are tail to tail. So they both have to be starting at A or B or C. Either one of those will get you the same results. Any questions on that one? I'm going to leave the calculation there, just cross product magnitude and divide it by 2. Okay. So the next one, good question here. This is what is the angle to the bank? And it says, would that imply you subtract 90 from the theta that you got? It kind of depends how you're calculating your theta, but the bank of a river is the edge. So it's like this edge part. So wherever you calculate what angle to the bank should she swim if she wishes to go directly across. So she wants her resultant to be directly across. We know that the current's going to be going that way and that this is going to be her swimming. So presumably you would find this theta here, right? Then you will, this is the angle to the bank, and that's exactly what you do. So you do 90 minus the theta. I think that that's how most people would solve that. On a test, I'm not going to be specific. I would just say, like, describe the angle that she would want to swim. And you could say, for instance, say you got 30 degrees for the theta that you had. So you could say 30 degrees upstream or 60 degrees to the bank. So it basically is different ways of explaining the same angle. So the 30 degrees, that measures how far you're pointing kind of from like a perpendicular, and the angle to the bank means how far are you measuring out from the edge of a river. Okay, so I think that that's probably the main question. You would have to figure out for B, you're going to find the magnitude of the resultant. Did you want me to go through that whole question, or was it just the wording there?
Ms. Cooper, I just have one question.
Yeah.
So you say 30 degrees upstream. I'm assuming we have to say the upstream, like we can't just say she's traveling 30 degrees.
Right. Yeah. Tell me which angle you're giving me. So it would be upstream if it's going like where the current comes from. If you had a different kind of question and you were saying like that you got some angle downstream, that would be like theta degrees downstream. Or you could say 30 degrees from directly across, or 30 degrees from perpendicular, whatever it was, but just describe where you're measuring that angle. I won't be too picky about the exact wording, but you can't just tell me, oh, she's at an angle of 30 degrees or 60 degrees. You have to say, like, what are you measuring that from? If you say from the edge of the river or from directly across, or whatever kind of wording you can do to explain that. Basically, whatever your words are that I read on your solution, I should be able to interpret that correctly and draw where that angle would be and understand it. Okay. So this one, for page 418, number 18C, the vector projection of n on m. So how do we want to format the answers for the test? Because I have the right numbers just in a different order. All right, so let's just try this one. So we know that the vector projection of n on m is going to be, we'd have the dot product of those two vectors divided by the magnitude of m squared times vector m. So we're going to need to do dot product of the two vectors divided by the magnitude squared, and then multiply that, make it a scalar multiple of vector m. So here I would do my dot product. I've got 2 times root 3 plus root 3 times negative 2. Oh, that's kind of nice. Plus negative 1 times negative 3 over the square root of, and here's where we get the magnitude of m squared. So it's root 3 squared plus negative 2 squared plus negative 3 squared. And then this whole thing is squared, the magnitude squared, times vector m, because that's what we're projecting on. So root 3, negative 2, negative 3. So in the numerator, I'm going to say 2 root 3 and then minus 2 root 3. Those things just disappear. So then I just have -1 times -3 is 3. And in the denominator, I've got this squared out here and then the square root. So those are going to cancel each other out as well. And inside there, I have root 3 squared, pardon me. So root 3 squared is 3, and -2 squared is 4, and -3 squared is 9. So here I get 3 over 16. Whoops, I'd still have this, root 3, -2, -3. So you always want to write it as an actual vector in lowest terms. So I'm kind of running at a space, but I normally would just go down here. So here I would have 3 root 3 over 16, -6 over 16, -9 over 16. And I guess I'd reduce that -6 over 16 to just -3. Whoops, I had 2 negatives in there. Just reducing that fraction to lowest terms, -3/8 and -9 over 16. So you always want to get it into component form and put your answers in simplified or lowest terms. Any questions on that one?
If we forget to simplify the terms, what mark will be docked? Would it be like communication, or would that be like the actual question?
Yeah, that this would be communication, that 6 over 16 is 3/8. But this is not a fully answered vector. You want to give me an actual vector answer, so you should multiply in that scalar multiple. So if you leave it here as that step that's circled there, that would be part of the question, there. And if you just forgot that, reducing a fraction, that's communication. Okay. So this one, determine the components of a vector that is perpendicular to these vectors. This feels like an easy one for question number 22, but sometimes they're just kind of written in the order. The components of the vector, that just means in component form, which is what we almost always just use, right? So it just wants the X, the Y, and the Z components. So your answer here is just going to be A cross B, and just write the answer in component form. But yeah, sometimes extra wording, if it just said determine a vector, sometimes that's less confusing, I think. Then there is a question here about the solution here. Can head-to-head vectors be perpendicular? The angle between them, when they're not tail-to-tail. This is a little bit tricky, and I see here DC would be the same there as BC. Now, this is a bit of, I guess, a bit of a kind of special case because it's perpendicular. So normally we're always measuring angles tail to tail, tail to tail, right? So if I had vector BC and then vector DC, I should have said CB and CD are perpendicular. But the thing about perpendicular vectors is that if you rearrange those and kind of put them like that, if this is vector DC and that's BC, if these were perpendicular, then these also will be. Now, normally that's not the case. Normally if we had, say, one, let me draw one that's like not perpendicular. So if I had a vector here and a vector there, and this angle was maybe a 70 degrees, if I wanted to figure out what the angles between those two vectors were really, I would have to put them tail to tail, so like moving this blue vector over, and then that angle would be 110 because it would subtract from 180. But if it's 90, then it's 90 on both sides. So it's only the case that you can do that if it's actually perpendicular, because then like the 90 and 90, it would be the same when you put them head to tail or tail to tail. Does that answer what that one was asking? Just going to check in the chat.
Oh, sorry. Do you mind just like taking up that question like as a whole?
Yep, no problem. Okay. So here we want to prove for a rectangle that OA dot OC, I'm just going to erase this other stuff. And I think it's important to kind of recognize that the O in this is that means that the origin is like somewhere totally different. So if I draw this rectangle, A, B, C, D, like that I've got some origin somewhere, and you can draw that sort of wherever you want, but I would try not to draw it somewhere specific. Like I don't want to put it in the middle of the rectangle, or you don't want to put it kind of right beside any one of those points. So I'm going to put my origin like out there somewhere, that I would have OA and OB and OC and OD, and those would all be separate vectors from the origin going to each of those points. So this takes really kind of a little bit of sort of thinking this through and planning, and just a little bit trial and error too, right? So I always like to start with the things that I know, and I'm just going to scoot this up out of the way. I would know that the vectors, because this is a rectangle, that those opposite vectors are of course going to be equal. But also it's not just a parallelogram with kind of equal and parallel opposite sides. I also know that there's 90-degree angles in here. So those dot products would be 0. Okay. So what I really wanted to do here is to sort of get a way of looking at each of these sides, like my left side and my right side. So for the left side, I had OA dot OC. And instead of having OA and OC, I tried to write them using the dot product with just one vector from the origin. So instead of OA, I said I'm going to call that OD plus DA. So kind of going along that path for the OA. And then for the OC, I said I'm going to keep that OD because then I can maybe use it being the same, that I might be able to simplify this a little bit. So here I've just kind of changing this, and I know I'm going to be able to use the distributive property, so that's OD plus DA dot OD plus DC. And sort of the trick that I'm seeing here is that when I do distributive property, that DA dot DC is going to disappear. And because that will be 0 because they're perpendicular. And also I've kind of reduced a little bit the number of vectors that I don't know anything about, because I don't really know where A, B, C, and D are in terms of the origin. I want to get stuff more in terms of each other, using more of the vectors around the rectangle is sort of my thought process there. So then when I distribute this, I get OD dot OD plus OD dot DC plus OD dot DA plus DA dot DC. And I know that DA and DC are perpendicular, so their dot product will be 0. So here I can kind of simplify that. OD dot OD plus OD dot DC plus OD dot DA. And then I kind of want to do the same on the right hand side. So I'm going to take a look at the right side here, and I started with OB dot OD. Now I like the fact that I've got, and I'm always kind of like looking to the left side or the right side and seeing what stuff I have in common, right? That I have an OD, and I have a lot of stuff involving OD on the first piece of the proof that I did. Now I don't really like, and if I just highlight here, I don't really like having this vector here going from the origin to point B, because everything else I've got is in terms of OD and then these guys, DC and DA. So this OB is kind of going off like into nowhere, that it's not connected to the stuff that I have on the other side that I've already worked on. There's multiple different ways of doing this. I just kind of picked the OD, I think, because of how I drew that. That was the one that kind of made sense to me first. So here, what I want to do is do a different path from O to B. So I'm going to probably make a huge mess of things, but I'm going to do like a green highlighter here and say, I don't want to say OB. This OB vector is not working for me in terms of it's not connected at all to what I have on the other side. But that OD vector on my right hand side, that's looking pretty good. I'm going to keep that. But the OB I want to put in terms of other things. So I'm going to say that that's OD, so going there, plus, and I could go different ways around the triangle, but I'm going to go DA plus AB. So instead of that one vector, I'm going to make 3 other vectors, which feels kind of like I'm making it messier. But now I'm getting things more in terms of the vectors I already have. So here I'm making the OB be OD plus DA plus DC dot OD. And then when I do this dot product and distribute that in, I'm getting a lot of the same stuff. So here I have OD dot OD plus OD dot DA plus OD dot DC. So that's looking really good, right? That if I take a look and kind of highlight the stuff that I have, this OD dot OD is the same on both sides. I also have OD dot DA on both sides. And the two that are different are not, oh, I thought I had to do a substitution here. Oops, sorry, this should have been AB. Sorry, I was looking somewhere else. Because that's the path I followed in the green there. So this would be AB. Sorry about that. So now these two look really similar. So here I've got OD plus dot AB, and here I have OD dot DC, but AB and B and DC are equal. So vector AB equals vector DC. So I can just do a substitution here. So OD dot OD plus OD dot DA plus OD dot DC, because I know that those are equal. And now I have like that third dot product that's equal on both sides. So I've got my left side equal to my right side. So general process here is that I didn't like the idea of having all of these vectors going from the origin, like all of these vectors coming out of the origin that I didn't know anything about. I wanted to simplify that into one vector coming from the origin and make the other vectors from the origin in terms of the vectors that are the sides of the rectangle, because I know more about those vectors. I know the ones that are equal. I know the ones that are parallel or perpendicular. Pardon me. Okay. Sorry, did I miss anything in the chat there?
I just have a couple questions.
Okay.
So dA dot product of DC, that is 0, why?
Because they're perpendicular.
So along with the AB and AD and the BC and DC,
Yeah.
the DA and DC are perpendicular.
Yeah, I said the other ones at the start, but then in my actual proof, I like squeezed that in down there because I hadn't listed all the pairs out.
Oh, okay.
Yeah.
So why did you put in the OD vector? Is it just to make it simpler? Like, make it more simple? Like, could you have used something else?
Right.
So
Yeah, you absolutely could have. So you could have said, like initially said, I want to make all of the vectors start with OA and then write OB in terms of OA plus AB and OC equal whatever. You could do it with any, but in general, I don't like having 4 vectors here that I don't know anything about, right? We don't know any kind of relationship between O and any of the points on the rectangle. So I wanted to get all of those 4, OD, OB, OA, and OC, in terms of just one of like the bad vectors that I didn't know stuff about.
Okay, that makes sense.
Okay, but you could have picked any one. I just honestly, like in my diagram, D was closest. So that's why I picked it. Yeah.
Then the way you did it in the left side, why couldn't you have done it on that way on the right side with like just batting it sort of thing? Batting both.
I kind of did the same on the right side, but because I picked to go to the point that was D, like from O to D, then this one was already in terms of OD, right? There. And OB, to start with an OD, you had to go along like what I did with this green highlight. You had to go along 2 edges of the triangle or the rectangle. So I had to do OD plus 2 edges. And here to get OA, it's OD plus 1 of the edges of the rectangle, and same for OC.
So basically you're putting it in terms of OD, but you already had that second term on the right side of the vector OD, so you didn't need to do anything?
Right, exactly.
Okay.
Yeah, I wanted to eliminate as many of the vectors coming from the origin as I could, so I wanted only one. Choosing OD instead of like OC or OB is just arbitrary. Sorry, question in the chat or no? Okay.
Yeah. So should we always put O like below the points? Because when I did it, I put O like in the middle of points A, B, D, and C, and then like I wasn't able to like rewrite like OB in terms of the 3 vectors.
You still should be able to, even if you'd drawn O like in the middle. Like I'll do it up in that top left because I'm running out of space here. But if you'd drawn O in the middle, then you could still do like OB is OD plus DA plus AB. It is still equal to that, but I think that it's harder to see.
Yeah.
And then some people, if you draw O right in the very middle, then I think sometimes people kind of accidentally assume things about where that O is, and kind of assume like, oh, these magnitudes must be equal, or this must be perpendicular, when like really you don't have any information about that.
Okay.
That I think is the danger of it. So I like to put it like out where it's very obviously not doing anything special. Okay. So I think that there was just one more question. So here, an airplane has a speed of 300 kilometers per hour and is headed due west. So the plane, can planes even stay in the air if they're only going 300 kilometers an hour? I don't know. So a wind is blowing from the south. So that's the key here, that it's coming from the south. So that means that the wind is blowing towards the north. So here I've got a wind coming from south, going north, and we want to determine the resultant velocity of the plane. So that's my resultant. This one's actually pretty nice because it's a nice like 90-degree angle. We don't even have any like weird things there. We don't have, you know, kind of to figure out like the off angles that we might sometimes have. So the resultant would be the square root of 300 squared plus 50 squared, the magnitude there. So that'll be 304.14 kilometers per hour. And then we'd also want to do our theta. So I would say tan theta here is 50 over 300. So there I get 9.46 degrees. But it is important to remember that we always give our angle references from north or south first. So I have to figure out what this angle is by subtracting from 90. So that will be 80.54. So I would just say, therefore, the resultant velocity is 304.14 kilometers per hour. And then the direction would be north, 80.54 degrees west. So always starting from north or south, you wouldn't say west 9 degrees north. You always want to start from the north or the south. That's the kind of communication convention there. Okay. Any other questions?